in calculus. Okay, so first we're going to start off with something really, really simple. So imagine you've got an XY plane. Okay, well that was ugly. Imagine you got an XY plane. All right, and let's say you have a line. We'll pick a couple points right there. Sure. Pick some points here. All right, how do you get the slope of this line? How do you get the slope? Well, it's the change in y, which we represent with delta, Greek letter delta, y over delta x, which is just a really fancy way of saying you take, let's say these have numbers. This is y1, sorry, this is x1, y1, and this over here is x2, y. Actually, we'll just use 0, 0 for, x2, y2. Okay, so x2, so you're just saying, all right, if I take y1 minus y2, divide it by x1 minus x2, it doesn't matter which one you put first, as long as these numbers line up. See, so the ones, if you do 1 minus 2, then you should do 1 minus 2 on the bottom. Real simple, right? So this is basic stuff. This is your slope. So what is that value? Well, here we have a value of 1, 2, 3, 4 by 1, 2. So this is 4, 2, and this, of course, is negative 4, 2. Sorry. Yeah, negative 4, negative 2, right? So if we go ahead and do the math, you get 4 minus negative 4 over 2 minus negative 2. And of course, you can do all this with a calculator and whatnot, but it's more important that you understand the process so you can figure out later, right? But this is pretty simple. You just have your values, right? So this is going to be, that's a 4 on the bottom, 8 on the top. So you have a slope of 2. Except I did that wrong. I did x over y. It's y over x. So you have 2 minus negative 2 over 4 minus negative 4, which is going to equal 4 over 8, or slope of 1/2, which is about right? Like here's 1, so if you go, and here's a slope of 0, so right in the middle is 1/2, right? That makes sense. And you can see that you would go, for every 1 you go x, you go up 1/2, or for every 1 you go up, you go over 2. See? And so we've picked 4, so we're going up twice. But anyway, that's slopes, right? The important thing is this delta y over delta x, right? Like that's the key thing right there, okay? Delta y over delta x, because now we get on to the first problem that calculus tries to solve. And this is, let's do another example. Let's say right here, this is 1, 2. I need some more line. So 0, 1, 2, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9 up there. Okay. And same thing on this side. We'll reflect it. Check it out. Get a parabola. Okay? It's a very ugly parabola, but the points are there, and that's the important thing. All right, so you have a basic parabola. It's curved. Now let's say I wanted to get a line that represents, as the line curves, we can think of it as a bunch of little tiny slopes all coming together, right? So what if I wanted the slope of one of these tiny little lines, this line that is tangent to that point? Well, we can approximate it, right? So let me draw this a little bit more clearly. 6, 7, 8, 9. All right, so we're going to use these to make it a little wider. So we're just going to look at the right half of it, okay? So 0, I'm going to change color. So at 0, we're going to have a point. At 1, we're going to have a point. At 2, we're going to have a point at 1, 2, 3, 4. And at 3, we're going to have a point at 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So, if we have our curve going through these points, I try to draw that smoothly, then we can approximate the slope. Let's pick a really curvy part like here. Okay, we'll pick it at 1, 1. We want this slope, right? Well, we can approximate that by, say, taking this point and this point, drawing a line between them, right? And that's kind of ish. In fact, it might be close. It might be really close actually, because the way it was done, right? So how do we do that? Well, we do change in y over change in x. I'm not going to do the example because you don't need to do the example. We just did an example of how to calculate slope, right? Well, it turns out we can actually get more accurate if we say, let me pick another color so you can see it. If we say pick a point here and a point here and draw a line, right? Let me zoom in. Let me erase this, not erase that. Yeah. Or if we picked points that were here and here and here and here, and you can see we're almost to that point, but we still have 2 points. So imagine if you had 2 points that were right where this point is. Just 2 tiny points as close as possible, right? What does that mean? Well, that means that our change in x is like 0. Dot, 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 1, right? Dot, 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 1, right? It's so small. It's what we call infinitesimally small. That word's not, you don't really need to remember it. You just need to know that I'm going to use it a lot. But so that means that our delta x over, or delta y over delta x is now going to become a tiny little change in y over a tiny little change in x, and we use d to represent that delta. And so this is right here, this is the derivative. Now, what's really cool about this is you can represent this with an equation. You can represent this with an equation, right? So the change in y over the change in x is the same as, and I'm going to use, instead of y, we're going to make it a function, f of x, okay? So the tiny change in f of x, which is y, over x is simply f of x, right? So that's your x1, or that's your y1. We can say f of x1 minus f of x2 over x1 minus x2, right? So we're going to represent this with a value called h, right? So what we can actually write this as is f of x1 minus f of x1 plus h, right? Because if you take x1 plus h, that's going to equal x1 plus x1 minus x2. Sorry, minus h. Minus that, which is, of course, x1 plus x2. And I did this wrong. What did I do wrong? That's the question of the day. Oh, that's going to give you x2. Right. So we're substituting this, which is actually this, for x2, which becomes that. So put that over h. So we can rewrite that as dy over dx is equal to f of x minus f of x minus h over h. All right. And remember, we want this change in x, right? H and dx are basically the same. We just use h because that's the typical notation, right? But we want to take that h and make it as small as possible. And that's where these things called limits come in. Now, limits don't need a whole lot of explanation. They really don't. They're really simple. If you have a line that's going like this, and then all of a sudden it has a little break, and then it continues down here like this, right? you think of as if there's a non-existent line in between them, right? The quote-unquote limit we represent with lim as x approaches 1, and we can say from the left using a negative sign or from the right using a positive sign. So as we approach from the left, where's it going? It's going here, 1. So the limit as x approaches 1 from the left is 1. And down here, if we come from the right, you notice it's this. So the limit as x approaches 1 from the right is, of course, -1, because it's this point. Right? Super simple. It's just where's the line going, right? So where's the line going, right? This is our y. We're getting our y. Where is this function going as h goes to 0? So we say the limit, the limit as h approaches 0 of f of x minus f of x minus h over h. So let's take our x squared example. We can plug in x squared. So we come down here. Let's pick blue. That's a nice color. Not as nice as green, but limit as h approaches 0 of x squared minus x minus h squared over h. All right, so that's the limit as h approaches 0 of x squared minus xh minus x squared minus xh plus h squared over h. So this will cancel with that. This will become positive. This will become negative. And then we take out an h. So that was really complicated math, but it means that you get limit h of 0 after simplifying of x minus h. Sorry, there's 2 here. I did that wrong. This becomes x squared minus 2xh plus h squared. Right. So you get 2x minus h. But of course, h is going to 0, which means h is going to be 0, which means 2x. And that's our first derivative. So we know that we can now calculate, if we have our parabola, the line that touches a point at some x. The slope of this line is 2x for this line, which is x squared. And that is true for any point on the line. If you want the slope of this one, that was not the correct line. So if you want the slope of this line, once again, it's 2x, but it's a different x, so it's a different slope. Now we can use this definition to calculate a bunch of different anything. You can use it on any possible function. But thankfully we don't have to, because at this point it becomes memorization. We can just go to Google and we can just type in like a derivative. If I could type go to Google, type in derivative chart, click on images. No, these are sine waves, but you get the idea. Yeah, here we go. So, as you see, if you take the derivative, don't worry about the right-hand side, just look at the left-hand side. If you take the derivative of a constant, any value in, it's always 0. If you take the derivative of x to the 0th, or just x, it's equal to 1. If you do x to the n, now we did x squared, right? So we had x to the 2, where n is 2. So we made it 2x to the first, which is just 2x. But that actually works. It's called the power rule. It works for any of these, right? E to the x stays e to the x. Natural log of x becomes 1 over x, and so on. You get this table. Now, it works a lot like you'd expect it to. If we go back to the... let me go back to notes. So if we go over to our example, which is x squared becomes 2x, then what does 3x squared become? Well, it's pretty easy. It becomes 3 times 2x, which of course is 6x. So that scales like that. Let's say you had, just for the sake of example, let's say you had x squared times x squared. Now you could just make this x to the 4th, right? And that becomes 4x to the cubed, 4x cubed. But there's other rules that you have to learn about when you're combining them. But again, these are just, you can look them up and memorize them. They're not, you have the, with this video, with this equation, with this equation, you have what you need to understand how it works. You're taking a tiny little change. The rest is just memorizing forms, right? So there's a thing called a product rule. And I'm going to mess this up. Actually, let's change this to be, sure, let's just have x. So it's x to the cubed. So this is going to be 3x squared, right? Using that same power rule. So you bring this down, and then you make it minus 1. So we get 3x squared, right? So to check our work, we're going to, on this product rule, we have what we're looking for. So the product rule basically works like this. You take this one, and you derive it. So derivative of x is 1, and you get this because you do x to the 1st, you pull this down, and you subtract 1, so you get 1 times x to the 0, which is just 1. So ignoring that, that's 1, and you times the x squared, and then you add this one, derive this one, 2x, just like before, and that's going to be times x. So of course you get x squared plus 2x squared, which is, just like you might think, 3x squared. So there's a couple of different rules like that. So the ones that you need to look up, you can just Google them, and it'll tell you exactly what you need to know. You need to know the power. You need to know the quotient rule, which is the opposite. So instead of x squared times x, you get x squared divided by x. So the quotient rule, quotient rule, you know what? Yeah. Power rule, the quotient rule, and you need to know the chain rule. This video is as long as it is, so I'll leave that to you to look up. And there you go. And that is the first half of calculus.